I want to thank the organizers for inviting me and not for inviting me, but including my talk in this. So I'm going to talk today about some of the work that we've been doing for last few years on charged polymers. And one particular aspect of the charged polymers I'll be talking about is collapse of these polymers and how the fact that they are charged makes difference in certain quantities like conformations and scaling laws, etc. So this is a very well-known for neutral polymers. The conformations depend only on the energy or the temperatures. So, and in good solvent, effectively, where the monomer-solvent attraction is higher than monomer-monomer, the polymer tends to be in an extended conformation, and the conformation which can be characterized by radius of gyration depends only on the n, which is the number of monomers in the polymer. This goes as 3/5 in good solvent, and in poor solvent, it goes as 1/3. Situation is slightly different when we go to charged polymers. Before I speak about the scaling laws, there is a very small introduction to what I call polyelectrolytes. These are the charged polymers, which are polymers with ionizable monomers, and when they are put in water, the charges separate, and you have a charged backbone, and there are counter ions which are in the solution. So the overall system is usually neutral. But these charges, I mean, I've shown here a special case of a very strong charged polymer in which all the monomers are charged. This need not be the case. For example, systems like proteins and DNA, the charge is more distributed. There are some neutral monomers and there are some charged monomers as well. So coming back to the conformations, as I said, the conformations that these charged polymers take are different from neutral polymers. So for example, this is a charged polymer in good solvent. The beads are not the solvent. These are the counter ions. The solvent molecules are not shown. If you see at very small charge density, which means it's basically acting like a neutral polymer, this is in an extended conformation. As the charge on the polymer is increased, the counter ions start condensing on the polymer, but it's still in somewhat of an extended state. And very counterintuitively, if the charge density is very, very large, the polymer actually collapses. So this is very different from a neutral polymer and also counterintuitive given that the polymer is completely charged. So the same thing happens in bad solvent as well, but I'm not talking about it here. So the heart of the problem lies in what is called a Manning condensation, which just compares whether entropy or the energetics dominate in the systems. When the charge on the polymer is very small, the entropy of the counter ion dominates, and they try to fill up the box and try to be as away from the polymer as possible. But when the charge is very high, the electrostatics dominate, they condense on the polymer, and this condensation somehow leads to the further collapse. There are many theories, I'm going to talk about it, but the fact that any collapse in this system starts with this process where the counter ions condense at reasonably high charge density. So there is this quantity called Jerem length, which I'll be referring to in the other thing. Basically, this tells you what is it's a competition between entropy and electrostatics, and it tells you where the electrostatics will win. So why is compaction of a charged polymer of any interest? There are many systems, the most well-known system being a protein folding problem. Usually protein starts off as somewhat of an extended structure. It goes into what is called a molten globule, and then it finally rearranges itself into some sort of a native structure. So these are the three things. First, it goes from an extended to collapse. There is no definite conformation in this collapsed conformation. It's just some kind of a molten globule. And then there is a local rearrangement, specific interactions take over, and that's when you get a native state. So we can represent all these processes with this kind of a very coarse-grained modeling, in which you can see that there is a very good complementarity between what is actually seen in, let's say, all-atom kind of simulations and your coarse-grained simulation. So basically, there is an interplay of charge and hydrophobic interactions that are in effect here. Okay, so this is the problem. A conformation, a single polymer charge, depending on the charge density, takes many conformations. It can go all the way from extended at extremely high charges, goes into something called a Wigner crystal, where there is an extremely well-defined crystalline structure that can form in these systems. And there are many questions of interest. What is the nature of effective interactions? These are charged systems, and still they form collapsed conformations. So what is the nature of the effective interaction? What is driving this attraction? What are the simplest models that can capture various phenomena in these things? What is a good theoretical description to understand this? And as a function of various parameters, you can include charge density, you can include flexibility, many other parameters. How do you understand this phenomena? And is there a way to characterize spatial and temporal correlations between the counterions and the polymer? So as I said, the scaling laws in neutral polymer are primarily driven only by the number of monomers. So an extended to collapse only goes, the Rg depends only on n to the power of 1/3. But in a charged polymer, in addition to this, in a collapsed state, the polymer, the scaling of Rg on n is still 1/3. But in addition, we have an additional scaling law that can emerge because of the charges. So now you have sort of two scaling laws, and the point of the talk is, what is this gamma? What is the dependence of Rg on the charge of the polymers? So there are many theories in literature. There is a theory, dipole theory, which basically tells you that when counterions condense, they form transient, temporary, or sometimes permanent dipoles with the oppositely charged monomers, and there's a dipole-dipole attraction which collapses the polymer. If that theory is to be true and you work it out, Rg scales as Lb to the power of -2/3. There's another theory, counterion fluctuation theory, which basically says these counterions are not really permanently sitting on the monomers, but they fluctuate. They introduce something like a negative pressure, which collapses the polymer. And if you work out that theory, the Rg is proportional to half. There's another one, ionic solid. Yeah. Yes. In what sense you mean by that? This is a charge density on the system. So we've actually shown that the perhaps, but in this case, I do not see why these two should be related. So in fact, we have shown that the critical charge density beyond which the collision happens is actually independent of n for a lot of the polymers. So maybe I'll discuss with you. So there's another one, ionic solid, where essentially there is no dependence of Rg on n. So we wanted to use molecular simulations to see which of these scaling laws is correct. So we set up an empty simulation where we take a chain length of 200. We have many counterions that we take into consideration. We do good and poor solvent. We don't include solvent molecules explicitly. It is introduced through the epsilon, the relation between the polymers and the counterions. There's no additional salt. And what we see, these are the main results of the simulations. We have, I'm not showing the poor solvent, we have poor solvent results as well. So what we see is that as a function of the charge density, your Rg, so you have a n 1/3 there, your Rg scales, we get L to the power of -12, which is predicted by the counterion fluctuation theory for all the counterions. But we also seem to get a new regime, which is not half, which is 1/5. This is not predicted by any of the three theories. Counterion fluctuation also doesn't have this. And one interesting thing is that what we see is also, if I look at the total charge of the globule, it's not exactly 0. It's 0 only after a particular A or an LB critical, and that seems to match with where these two regimes seems to appear. So how do we explain this emergence of a new scaling law? What we can then go back and do is, if you look at the free energy of this, in a collapsed phase, you have the entropic term we are ignoring, you have the volume interactions and the electrostatic interactions. This is the electrostatic interaction. In the original counterion fluctuation paper, this kind of scaling law was obtained by including only the second virial coefficient. But now, if we go and include the third virial coefficient and minimize with respect to Rg, you get an Lb to the power of 1/5. So then the counter-ion fluctuation was actually modified to include this new one. In fact, the situation becomes more complicated in pore solvent because you have an additional interaction that is coming between the monomers. So we see that the counter-ion fluctuation theory is the one that describes fairly well the simulation results that we see. And in addition, we actually get a new scaling relation in good solvent. As I said, in bad solvent, we actually see signatures of more and more virial coefficients. We cannot exactly separate the contribution of these different virial terms, but we do tend to see that more and more virial coefficients are included. You get more and more deviation from these scaling exponents. So the summary is, in the collapsed phase for the good solvent, we shouldn't think of this collapsed phase in charged polymers as a single entity. There seems to be many regimes. In good solvent, there seems to be only two as far as our simulations go, but in poor solvent, we do tend to see many, many more phases. So we characterize these two regimes as weak and strong. We can look at this weak and strong. One point of view is the total charge of the globule. That seems to be different in these two cases. These MD simulations, they helped us identify what is the right theory of the attraction, which seems to be the counter-ion fluctuation theory. But of course, we have not physically shown that what is the origin for these things. We've only sort of eliminated the theories which probably do not correlate well with what we are seeing in the simulation. So what we are trying to do now is to look at, understand and quantify the mobility and correlation between these condensed counter-ions. In fact, there's a nice talk by Dr. Ghoshal in the morning where we could probably now look at these counter-ion distribution. These are just the counter-ions which are shown. We're showing counter-ions in one form of a configuration when the polymer takes a particular shape versus another one. We could think of this and probably use normal mode kind of calculations to look at glassiness of these behaviors and to how to go from sort of Wigner liquid to a Wigner crystal kind of structure. And that is the work that is on the way. So I want to thank Rajesh. We've been working on this problem for quite some time now. And we, as a graduate student, he worked on it. She has a poster. And Nikolai Brilliantov, he's the one of the authors of the original counter-ion fluctuation theory, which is. Thank you.
Do we have questions?
Like RG poses L to the power minus half.
Yeah.
So that is the fitting is only 12 to 14. So can you trust this power law? Just something which is from 12 to 14.
You mean on the A?
Yeah. So can you go back to the
yes.
Here? So you can just look at, like, L to the power 12, just 10 to 14.
Yes.
Or we 10 to 13.
Yeah. You don't trust that result. You're saying it's a stretch to call it a scaling law. Is that what you're saying?
Yes, stretch to call it a power law.
All right. That's probably true.
Any other question?
Yes.
Can you tell whether this model has accounted only for the charged residues as well as for ones that are polar but not exactly charged?
So what you mean, so I showed something in the beginning where we have everything is completely charged. So we have a system where you have plus and minus. There's no polarity that has been introduced into the system. But one can play with this. We can introduce some fractional charge into the system. We have not done that, but that's doable. But we've not attempted that. These are just strongly charged polymer systems.
Let us then thank the speaker.